PhD student in geography, and Heather Summers, who's a master's student in geography. And Heather is going to introduce Douw, who's well known to many of us, but Heather, over to you.
All right, welcome everyone. So before I begin introducing our speaker for tonight, I'd like to acknowledge that we are situated on the traditional, ancestral, and unceded territory of the Musqueam people, and we are very grateful to be able to be here tonight, and we thank them for their hospitality. So tonight we are privileged to have Dr. Douw Steyn here. Dr. Douw Steyn, he is a professor emeritus of atmospheric science at UBC in the Department of Earth, Ocean, and Atmospheric Sciences. He's also a member of the Institute for Applied Mathematics, the Institute for Resources, Environment, and Sustainability, and the Liu Institute for Global Issues. Now, in addition to his academic appointments, Dr. Steyn has served as Associate Dean in the Faculty of Graduate Studies and Principal of the College for Interdisciplinary Studies. Now, Dr. Steyn told us that a great source of satisfaction in his career has been the students he's had the pleasure of working with. He enjoys devising new courses and structuring curricula at all levels. And during his time here at UBC, he has developed 15 new courses. Now, he's won the UBC Killam Teaching Prize, the Canadian Meteorological and Oceanographic Society Andrew Thompson Prize in Applied Meteorology, and the Canadian Federation for Earth Sciences Mentorship Medal. Now, in addition to all the work he has done with the university, Douw is an accredited consulting meteorologist and has international consultancy experience in his areas of expertise, and has provided expert testimony in court cases and appeal board hearings here in British Columbia. Now tonight, Douw will be talking about the two ways he has gained satisfaction from his work. So the first one has been as a physicist. So he enjoys solving problems and finding out how stuff works, and he does this using mathematical models, mathematical techniques such as modeling. And this work gives him the intellectual thrill of solving a problem, and in order to illustrate this, he will talk a little bit about his work on Seabreeze. And then the other source of satisfaction is from producing research results that are relevant to society. And the example he will give of that engagement is the work he has done on modeling ozone air pollution in the Lower Fraser Valley. Now, an interesting fact that we learned about Douw is that he has a passion for woodworking and enjoys sailing small boats. So when we sat down with him earlier this week, he showed us some pictures of a bicycle, a clock, and a sailboat that he had made out of wood. So that was really interesting. So without further ado, here is Dr. Douw Steyn.
Thank you. Thank you. Thank you, Heather, for that lovely introduction. So with that, we're all done. Are there any questions? Yeah, well, so there we are. This is a career in retrospect, I suppose. Just let me get the case on the back of this thing before I drop the battery. Yes. Yeah, so where did that start, Ralph? You know, I can remember at the age of about 4, I was given this beautiful red plastic tractor. There was an advertisement by the Massey Ferguson company. And somehow my father got hold of it and gave it to me. He was horrified when I took it to the bottom of the garden and laid into it with an axe. I wanted to see how it worked. And I suppose that really tells the thing about solving puzzles. I got whipped for that. but nevertheless, it was only in retrospect I understand what was going on there. And all of this is, of course, in retrospect. Yes. No. Are we in the slide viewing thing? Are we in the advance? Is the battery plugged? Ha. There we are. So what am I? What am I by nature? Oops. Okay, shall we try the traditional way? By education, I'm a physicist, and I suspect by nature as well. What does that mean? It means I like to find out how things work. I apply a very particular set of tools to the working of things. Those tools are, of course, mathematics. Good or bad, mathematics is enormous simplifications. and in this case, simplifications of an enormously complex thing that is the atmosphere. I'm an atmospheric scientist by application. Many physicists will think I've gone to the dark side, working with this application, indeed dealing with one of the core subjects in the atmosphere, which is studies of turbulence, which has now quite formally been declared not part of physics, because it is not really a soluble problem. But it is an important problem, and it is important because in the atmosphere, it is what is responsible for the movement of whatever is in the atmosphere, movement vertically, movement horizontally. And that movement is, of course, what makes air pollution bearable, because it moves away from the source, away from our lungs, away from us, and becomes diluted. The question, air pollution is diluted. By inclination, I'm an environmentalist, unashamedly so. I think this is because I grew up in an extraordinarily beautiful place, a small town in the south coast of South Africa, on an estuary, flanked by a huge forest, feet in the mud, feet in the water, looking at clouds, messing around in the environment. And I believe this engendered in me a sensitivity for the environment and for the beauty and wonder of the environment. And all of these things have come together and in some strange ways define what I study and how I study it. So let us then first deal with air pollution meteorology. Air pollution meteorology is what pollutions do in the atmosphere. There are three parts of meteorology, of air pollution. How it's emitted, that's some factory with an engineer at the bottom of the smokestack. What happens to it in the atmosphere? It's spread around, it's diluted, and eventually it becomes deposited and is absorbed in your lungs and mine, which is where the health effects happen. I do the middle stuff, where it starts in the atmosphere and where it ends up on Earth's surface materials. So I deal with atmospheric turbulence, as I've said. That was quite central in my PhD here at UBC. The atmosphere is filled with motion at a wide range of scales, and it is impossible to make any movement forward without acknowledging those scales, without using the scales, and performing a scale-based analysis. And that was part of my PhD. And thirdly, the bottom layer of the atmosphere is called the atmospheric boundary layer, the planetary boundary layer. It is where everything happens, where human beings live, where all organisms live, where the exchanges between Earth and atmosphere occur. That is the functional part of the atmosphere. All the rest is will background and backdrop, in my opinion anyhow. And that too is part of my PhD. In order to complete air pollution meteorology, you must understand dispersion of pollutants, the spread, the dilution, the transformation, chemical transformation. And that is interesting because up until more or less the beginnings of my PhD, atmospheric science was a domain of fallen from grace physicists. It then soon became the domain of fallen from grace chemists with the granting of the Nobel Prize to Molina and Sherry Rowland. And it was at that stage that we realized that the chemistry of the atmosphere was at least as important as the physics. Indeed, pollution moves around, but its movement is very strongly conditioned by the effects of complex terrain and coastlines. And then there are all kinds of applications in which all those branches of the science come to focus in a real problem. What happens here? Why is it polluted here? Why is it not polluted there? How polluted is it? How much can we emit into this airshed and still survive? There's a little picture. You can see all that I've spoken about in the little cartoon drawing. So this started, and here is the first part of my story. Oh, and then let me admit quite openly to me that little aphorism that life only makes sense when lived backward applies excruciatingly well to me. Don't ever believe that all of this was some guided thing that happened from the beginning of my PhD with an established trajectory with known stopping points and a final point. It is not like that. This is what Gerald Holton called public science rather than private science. Private science being the mess that happens in your head with all the distractions the sidetracks, the confusions, and then at the end we write it up in a nice clean story. Isn't that neat? So we admit fully that that's what happens here. So I was asked to be an expert witness on an environmental appeal board that happened in Port Moody in the early 1980s, and there was supposed to give witness, and did give witness, on problems of ozone pollution in the middle and the central parts of the Fraser Valley. There was a crisis in the Fraser Valley, quite frankly a crisis. The ozone air pollution levels on odd occasion exceeded 200 parts per billion in the mid-Fraser Valley when the Canadian health standard at that age was 80 parts per billion. A condition in which quite severe health effects will occur over large portions of the population, not just the infirm or people suffering respiratory distress. The appeal board rejected our advice that ozone in the region was governed by local emissions and was involved in a local cooker of air pollution in a fairly complicated way, but was amenable to local control. And it's in the record, you can actually find it if you Google hard enough, that the chair of the appeal board said, we do not agree with Professor Steyn, Dr. Steyn at that stage, was it? Just Professor Steyn at that stage, that the problem is locally caused and locally soluble. And yeah, that hurt, because I was pretty well convinced I was correct in my judgment at that stage. Though it was a judgment made without a heck of a lot of science. So let me tell you where the science came later. So this is the history of air pollution in False Creek. Around 1900, that's what it looked like. Now this is a picture from the city archives. You know, the old black and white photograph has been creased and looks horrible, but it was indeed, the city was locally covered by a pall of smoke from pulp mills, sawmills, and the burning of waste wood around the False Creek area. This is, you know, this is looking straight past where Granville Island is at present. That was relatively easy to solve. This is what happened in the 1980s and 1990s, which was the result, which caused that 200 parts per billion of ozone. It is a regional haze consisting of both ozone and very fine particulate matter. The particulate matter resulting from chemical reactions in the atmosphere in which gaseous pollutants combined to form very fine, inhalable, deeply respirable particulates. So there were episodes of this pollution, this regional haze, and they were closely linked to the occurrence of sea breezes. The simple reason is that they're common antecedent conditions. Conditions for a sea breeze were warm temperatures, strong sunlight, light regional winds, and of course those warm temperatures are what produced the chemical reactions, well, not produced, but accelerated the chemical reactions that resulted in this haze, and the sea breeze movement determined the distribution of the haze. So as a young faculty member with a handsome NSERC equipment grant of $15,000, I set off to try and gain a deeper understanding of the sea breezes. So now this is where I'm reconstructing my career backwards. The red ones are ones that I'll pay some attention to. The black ones are things that I'm going to skate over. And probably the most important part of this slide is to recognize the collaborations with an amazing range of colleagues, faculty colleagues, government scientists, and particularly graduate students. So the bits I'm going to talk about are how to understand the sea breeze occurrence and structure generally, and then specifically in the Lower Fraser Valley, and then how to model the spatial and temporal structure of ozone in the valley. And of course that was the crucial question that was in front of the appeal board. What is the spatial distribution? What is the structure? And how has it changed over time? And most importantly, how can we manage this thing? What do we need to do in order to improve air quality conditions in the valley? I'll skip over the first part, which is a strictly statistical analysis done with a group of fine statisticians and grads. Excuse me? The atmospheric boundary layer, excuse me. My field is littered with impenetrable acronyms. And then the third one is the understanding of the spatial and temporal variation of the atmospheric boundary layer, which is the layer in which the pollutants are trapped. So I'm going to ignore those two and just take a quick walk through number 2, and number 4. So there is the sea breeze. So the big question you have to ask when you want to investigate a sea breeze is, when is a breeze from the sea not a sea breeze? Just because it comes from the sea doesn't mean to say it's a sea breeze. All this implies is that a sea breeze, properly constituted, is a particular geophysical flow phenomenon. And its particular characteristics are that it is a wind that blows towards the shore, sea breeze, at low levels, but above, somewhere around 1,000 meters or so, it blows away from the sea. And those two breezes, toward the land and away from the land, form a closed circulation. And it takes no great intellectual leap to realize that pollutants emitted into the landward moving part, low level, which is where pollutants are emitted, will just cruise up and then come back and hit you in the back of the neck later on in the day. And that, in fact, is precisely why we suffered air pollution episodes in this region, which actually has very small emissions by global standards. And it is key to understanding how we're going to manage this thing. And it's key to the understanding of the episodic nature of the sea breezes. So I set out with 2 grad students and $15,000. And I bought a pile of equipment, a set of local meteorological sensors on aluminum towers, which I sprinkled around the valley like confetti, and one instrument for probing the vertical structure, that vertical structure. I was kind of interested in that. The interest was purely, how does this thing work? Like the red tractor. So there's what the balloon looks like. It's tethered to the ground by a thin Kevlar line about 1 kilometer long. And at the bottom is a winch. And just above the winch there is a little instrument that measures wind, speed, direction, temperature, and humidity. That's all. And then you reel this thing out through the sea breeze, and then you drag it back down again. And you start at 6 in the morning, and you end at 8 in the evening, and you're hot and bothered, and the public around says, "What's that thing?" And it's great fun. And I did that for, 5 summers anyhow. Every time there was anything that looked like a sea breeze, I went out and parked that thing. Where did I park it? Well, every place that I thought my instincts told me was a good place to probe the sea breeze. And then one day, I was sitting there on a lawn chair. We carried little foldable lawn chairs with us. Got pretty hot and steamy out there. Sitting back, and I looked up at the line, and hey presto, the line was heading off east. And then it turned around, and above me, it was heading off to the west. And at that point, I said, "Oh, look, I have captured a real sea breeze." So at the end of those 5 years of summers, some hundreds of those profiles, I set off on study leave to the CSIRO, the government research labs in Canberra, and sat down with this entire pile of data and worked my way through the data in order to understand the vertical structure of the sea breezes. So there is a little picture of one of those profiles. Let me explain the details. This is a somewhat complicated map. So that instrument gave me 4 variables: wind speed, wind direction, temperature, and humidity. And so all 4 of those are plotted here on the same plot against elevation, vertical. So 0 meters to 1,000 meters. The balloon got up to nearly 1,000 meters that day. Anybody who's thinking now will say, "Oh, what about aircraft?" Yeah, we had to get air traffic clearance control and all kinds of complicated things. So here is wind direction. Look, it's blowing 270 degrees from the west. And then suddenly around 600 meters or so, it swings over, and there it blows from the east. But it's quite variable. It kind of flops around. There's turbulence. Here's the wind speed. Well, it looks like it goes to a peak, goes to a minimum, and then goes to another peak. There's the lower layer inflow, and there's the upper layer. Here's the temperature. Actually, it's potential temperature. It's a rather strangely convoluted way of looking at temperature. Meteorologists have odd habits. But it shows this is the atmospheric boundary layer, that strictly vertical part of the profile. And there's the upper part of the atmosphere. And humidity does exactly the opposite thing. Humid here, quite dry aloft. So there's an example. So I sat down with a fair collection of profiles like that. Now we've got to find a way of putting them together. Well, it's very simple. We'll just pull out the right mathematics, won't we? Those are the equations which govern that sea breeze. The sea breeze is a solution to those equations, not a solution that occurs in a mathematician's head. It is a solution that occurs in nature. Those equations are enormously complicated. I think there's $1 million prize, isn't that right, Cindy, for someone to show that there exists a solution in a closed domain. Not find the solution, just tell us if there is one, please. Still $1 million waiting for that. Those are called the Navier-Stokes equations. Very simple. This is Isaac Newton. First two are conservation of momentum, east wind, east-west wind, north-south wind. Vertical wind is the third one. And then conservation of temperature and conservation of mass. That's very simple. Nothing can go wrong. Trouble is that they're not soluble. So what do we do when we face a mess like that? Well, we try and find some approximate regimes in which we can say something useful about the equation. So if you look carefully at them, you'll discover that there are 5 internal variables. These are things that the equations generate, and these are things that come from outside. For instance, the drag of the air against the Earth, the amount of heat that is put into the atmosphere, the temperature difference in a horizontal that's driving it, the stability of that temperature layer over the top of the mixed layer, gravity, and that's buoyancy. Earth rotates, and rotation of Earth must be important here. And indeed, there's a diurnal cycle. That omega is the frequency, the diurnal frequency. All of those are internal. What do we do with it? Well, we sit and look at the thing for a while, and we say, well, what I've done here is I'm measuring all of those quantities using completely arbitrary units, meters, kilograms, seconds. Those are arbitrary. It's, a meter started off with the length of somebody's arm, goodness me. So what are the real measures that we should use when we're trying to analyze this thing? Well, the measures are those that will reveal the sea breeze. They are what we call the scales of the sea breeze. And those scales must come from the forcing variables. So I spent a while in the second half of that study leave in Japan. The first half in Australia, where Stuart Turner gave me great advice, a tremendously wise and very smart fluid dynamicist. Gave me some advice about how to construct these scales. They're effectively units of measurement that are specific to the sea breeze. You can't get a ruler like that. And it wouldn't be any use, because the only thing you could measure with it would be a sea breeze anyhow. You wouldn't want to measure the length of your car or the side of your yard with it. You only measure sea breezes. And the vertical length is different from the horizontal length. That's reasonable. The atmosphere is a very squished thing. Yes, Mark, it's messy, isn't it? Okay. And so what we do then is we say, okay, now let's measure the equations. Let's express the equations as they would be if we use these rather than meters, kilograms, and seconds to measure the quantities. And what happens then is you get a set of dimensionless equations. And I acknowledge my colleague Itsushi Uno, who sat at the back of an early seminar scratching his head. And it was clear that he didn't like what I was saying. And eventually when I finished the seminar, I said to him, Itsushi, what's gone wrong? And he just dropped 2 words on me, and the light exploded. And this is the final form that it came out after thinking about what Itsushi had said to me. And so what happens with the equations is you get all the same terms there, the u velocity, the v velocity, the vertical, and so on. But all of these have got stars because they have no units, because they've been measured using units specific to the sea breeze. But what appears is these funny pi things, and there are 4 of them. Those pi's are then the governing quantities of this equation, of the set of equations. So we started off with 7 plus 5 is 12, and we've got to 4. That's very useful, an enormous simplification of the matter. But you still can't solve them. So what you do is you say, well, do I have any measurements that will tell me something about those? So this is the way we proceed. They're the 4 dimensionless parameters. You can see they came from those governing variables. And the theory of dimensional analysis tells us that everything must then collapse to some equation of that form. The 4 pi's, products of powers of the 4 pi quantities. And the thing on the left is the phi SB is some quantity phi, any quantity of the sea breeze, divided by its own appropriate scale, must be a function of that form. How do we find A, B, C, D, and E? Well, very simple. We go and fit some data fit those formulae to the data and find them. So they're the scales for height and velocity, and those come from this kind of statistical analysis. Now, the physicist in me is horrified by this thing because, well, the points are all scattered all over the place. Why don't they just fall nicely on the line? Sorry, the atmosphere is a messy place. There's all kinds of other stuff happening. There are little waves occurring that we didn't know about. There was some kind of skewing of the wind due to a storm that was up the coast. And no matter how you try, you can't remove them. But nevertheless, those two straight lines, one for the height of the sea breeze and one for the speed of the sea breeze, the mean horizontal speed. Those straight lines are statistically significant if you take a probabilist approach to it, and they are meaningful. And there we are, the two scaling laws for sea breeze. Air pollution seems quite a far way away, but we'll get there. What you can furthermore do with that is I can take all of those profiles of the wind speed through the depth of the atmosphere, and I can non-dimensionalize them, and hey presto, they all fall on the same line. This is a universal sea breeze profile. It is true for all sea breezes, any place you like to call, any latitude, in fact, any planet. If you can find a planet with a sea breeze on, it'll form this. So this makes the little physicist's heart in me glow. And you can sit there and gloat over this thing and look at it for a while and say, that's really pretty. That is tremendously satisfying. And it is. It is satisfying. It is a sort of warmth in the gut kind of satisfaction. Something like solving a difficult Sudoku, but maybe with a little more relevance. And the universality of it, of course, has great appeal. And recognize that physicists are very, very simple people. You know, they say that a biologist is someone who knows the world is made up of thousands of things, all of which are essentially different. Mouse, elephant, microbe, fir tree, they're all different. They all have their particular characteristics. Chemists are people who know that the world is made up of only 104 different kinds of things. Hydrogen, helium, lithium, beryllium, boron. And that, once you know that, it's all. Physicists are people who would like to demonstrate that the world is made up of only one kind of thing. We're very simple people. So any achievement of what looks like universality appeals. So, the inner physicist in me is satisfied with this. I now understand the vertical structure of the sea breezes from my measurements with the network of instruments. I understand something about the horizontal distribution of the sea breeze, how it evolves through the day. And then we're going to start to use that knowledge to understand the air pollution episodes in the Fraser Valley. And the tool we use to understand these is a large set of numerical models, extraordinarily complex. I'll explain them in a moment in the next slide. Those models must capture the emission from all the sources, human beings, you know, dry cleaners, motor cars, pulp mills, cement factories, motor cars again, lawnmowers, dry cleaners, oh, I said dry cleaners, lawn blowers, and so on. Then you must understand the spread of these pollutants, how they moved in the sea breeze inside the boundary layer, and then how they are transformed chemically to finally result in the ozone. Ozone is not emitted. It's formed by a combination of pollutants that are emitted. So the work is not at all intellectually satisfying. In some ways, you can get any darn answer you wanted because the models are so complex. But if you have an understanding of the forces driving the atmosphere, you can constrain the models so that you get to a point where the model itself actually reflects what is happening in reality. And that is not a simple task. The models alone are difficult to run. They use large computing power. There's Ian McKendry at the back who started with me on this. You know, in that era, it took you about 6 months to get the model properly running in the computer. It took about another 6 months to figure out what the model actually meant, and only then could you start interpreting what it meant in relation to air pollution. So there's no great intellectual satisfaction because of the squishiness of the whole thing. However, it is satisfying because there are important questions that are of societal relevance, particularly if you can present your results in a way that can be understood by policymakers. So here's a very simple depiction of the model. So there's a little chunk of the landscape. Underneath, on the surface, are humans and all their activities, factories, cars, whatever, highways, land surface emitting from paddocks and fields, trees particularly. All those emissions from these four sectors are then mixed in the atmosphere, and the model consists of a number of vertical layers. I've only shown 3 here. There are many, usually upwards of 20 layers, to properly handle the lower atmosphere as well as the overlying upper atmosphere. You have to inject wind into this model, into this grid, and in order to inject the wind, you have to solve those ugly equations numerically, not with pencil and paper. You have to solve them numerically in order to understand how the wind moves through this, how the sea breeze circulates, where's the level of recirculation, how far does the sea breeze penetrate inland before the pollutants are returned. And at the same time, you have to have a set of chemical reactions, and there's only the simplest one. This is how nitrogen dioxide reacts, decomposes and reacts with ozone to form nitrogen dioxide itself. So there's a circular chemical reaction there, which immediately implies it's highly nonlinear. You can't just say doubling of the pollutant will produce a doubling of the ambient air condition. So there are many, many equations. All of them are approximations to a certain extent of the actual chemistry that happens, simply because there's no computing power to solve every equation in detail, and many of the chemical reactions are not particularly well known, so we approximate them. A messy business. Here is one simple map output of that chemical model. So what we have is the ozone field in the shades of brown, and the wind field in blue trajectories. So you see the sea breeze is not a simple thing in the horizontal, let alone the vertical. This one is for an episode we studied in 2001, and in August, August is when sea breezes occur most frequently and the ozone pollution is most severe. And you will see, the green triangles are the stations where Metro Vancouver, who's the regulatory agency, measure ozone pollution. And you will see that in this case, the sea breeze started from the south in the morning and carried the pollutants up over the North Shore Mountains. And amazingly, the network of little green stations actually is not really resolving the ozone very well. That was part of the reason why the Environmental Appeal Board was confused, that they were relying entirely on the network as if it was a realistic picture of the true ozone distribution. So the modeling exercise consisted of multiple modeling runs of a whole series of episodes which had been chosen specifically in order to represent the general conditions. What you do then is you put together all of these episodes and try and understand the chemical dynamics. So here is another messy business. Ozone comes about as a result of chemical reactions between oxides of nitrogen, which are emitted by any combustion process, and any volatile chemical compound, starting with methane, which is actually relatively inactive, but anything that evaporates out of the exhaust pipe of your car, or from the dry cleaner, or from when you fill the gas tank of your car and smell the gasoline, all of those react together. And the details of the reaction depend crucially on the ratio of the oxides of nitrogen to the volatile organics. So, where are these emissions occurring? Well, they occur where the people are. What has happened to where the people are? In this valley, they have shifted eastward. So the shading, the little squares, indicate population changes between 1985 and 2005, which is the span of our modeling. And they go from about minus 0.5% in the dark blue around downtown Vancouver, which has deflated its population. And the population has shifted eastward. Largely growing in Surrey, as we all know. And that change in population had to be incorporated into the model as part of the emissions. The crucial part is the blue and red lines. In 1985, the line between an excess of oxides of nitrogen and an excess of volatile organic compounds was there. By 2005, it had moved further up the valley, simply because of the eastward shift in the population, and to a certain extent because of changes in the chemical mix of the emitted pollutants, having largely to do with the introduction of catalytic converters in vehicles that were sold over that period. So here we have a very useful tool. We have a way of understanding the chemistry as it relates to the emissions. And the emissions are the things that you control. The emissions are what Metro Vancouver has to deal with. They are the items for which Metro Vancouver has an air quality management plan. And this is common to all regulatory domains in the world. So, what are the conclusions? Firstly, the western Lower Fraser Valley and Port Moody is in a VOC-sensitive location. They don't care about how much oxides of nitrogen is emitted there. It's the volatile organics that are important there. The central Fraser Valley in Chilliwack has changed. It used to be VOC limited. It's now NOx limited as population and emissions have shifted eastward. And then the eastern Lower Fraser Valley around Hope has been and remains still NOx limited. This is a hugely important result, particularly as some of you will recall, there was a proposal to put a natural gas-fired electricity generator in Chilliwack, which would have emitted enormous amounts of NOx. And my good colleague Ian McKendry was involved in that, in the opposition to that particular development, and correctly so. The development was stopped. It would have been disastrous. Hope is one of our regions, one of the places in this region that is still only just in compliance with the Canada-wide standards for ozone. To have emitted more NOx there would have been disastrous. So these 4 bullet points, wait a second, and then the last one is that the ozone production efficiency, because this reaction is circular, it's a cyclical reaction, it turns out that emissions of nitrogen oxide are repeatedly used in the cycle of reactions to produce ozone, and the number of times they use is called the NOx efficiency. And the NOx efficiency has increased around Chilliwack. That is because of the change in the mix of pollutants. And ultimately, the offsets from reducing local NOx emissions have actually been reduced in importance because of that change. So there's a complicated chemical fact that absolutely has to be included in any attempt to manage this pollutant in the region. So we've had a roughly 45% reduction in the ozone precursor emissions in this valley. It's not uncommon worldwide. Much of that is due to improvement in automobile emissions, improvement in the efficiency of automobile engines. But actually it has had a relatively little improvement in ambient pollution, mainly because of bullet number 4. And these kinds of discoveries are very direct guidance to Metro Vancouver's integrated air quality and greenhouse gas management plan. I see the latest report from them makes makes implicit mention explicitly of these discoveries. So that's satisfying. So solving the puzzle is satisfying, as I said, for intensely personal reasons. And the knowledge that I have gained, that we all gain from solving those sorts of puzzles, finally come to fruition when you can apply them to some problem of societal relevance. So an enormous privilege I think I've had to derive satisfaction from both kinds of my research. And then of course there's a very different kind of satisfaction that I've barely mentioned, only in passing with the few grad students I've spoken about. I have been tremendously privileged to enjoy my teaching, and as a result of teaching at UBC, and closely tied to that teaching, of course, has been the fact that I have produced research which is relevant in the courses I have taught, not necessarily at a high level, but in a very general way. And that research has put me in a privileged position of being able to provide consultancy advice to a variety of communities and in society at large. That's been enormously satisfying. And finally, just to emphasize the satisfaction that comes from teaching wonderful students at UBC, there's Ben Weinstein, Nadia Mosieva, and Annie Seagram, 3 of my last stage graduate students who accompanied me to this conference. Annie did a fascinating thing. She answered a question that Ian McKendry and I have been posing. And again, Ian and I used to shoot our mouths open and say, oh, pollution recirculates. pollution recirculates. So we put Annie the question, so what is recirculation? What does it mean? And can you actually demonstrate that it happens? And Annie took those model runs of the Seabreeze and traced particles numerically, traced particles through the Seabreeze, and showed how they returned repeatedly, some of them 4 or 5 times, back in the same cycle of Seabreezes over 5 days, which is about the length of our most severe episodes. So it's, it's to them that we derive enormous satisfaction as well. So there, I've said enough. Far too many details. Thank you for listening to me.